Alright, so now that we've gone through the abstract nonsense garbage that we had, we can actually sort of go through and go through an example and see exactly what I mean by this. So again, let's say that you have your xy plane. You're going to have two x coordinates, a and b. You're fixing 2 points, a, and b. Okay. And then you have, say, a couple of curves here. Obviously, a straight line is going to be your optimal curve, but I just threw a couple of examples. And so these are all functions y, and we're going to consider the functional j of y is equal to the integral from a to b square root 1 plus y prime squared dx, which represents the arc length of your curve on the right there. So what we want to do is we want to find an optimal value for this, which it'll turn out is the minimum value, and we'll only find one solution, subject to the conditions that y of a is equal to a and y of b is equal to b. So what we want to do is we want to look for something that looks like j of y plus h, or y0 plus h minus j of y0 is equal to some delta j, and so range delta j of h here. Remember that there is an implied y0, but because we want to focus on what I'll call the augmentation, so I'll just call h the augmentation. Since we want to focus on that, we're going to consider this depending on h, and then we're going to have plus epsilon times magnitude of h. So again, this epsilon is a function of y0 and h, and the idea is that these are sort of quadratic or higher in h. Okay, so remember that right now we're considering functionals of the form j of y is equal to the integral from a to b of f of x y prime dx. And so the f is just some function of 3 variables, so you should really think of this as f of x, y, z, and we're saying that we're replacing the z variable with y prime, and we're evaluating this at every point x, and then we're integrating that over, and then that'll give you some value for your functional. And again, this is of this form where you take f of x, y, z to be square root of 1 plus z squared. So what we want to do is look at j of y plus h minus j. Actually, I'll just write j of y plus h instead of y0. So j of y plus h minus j of y. So this will be equal to the integral from a to b of f of x, y plus h, comma, y plus h prime, dx minus the integral from a to b, f of x, y prime, dx. Okay, so here what we did was this, you're just replacing everywhere you see y with y plus h. So here you have a y and y prime. So here we have y plus h and y plus h prime. So y plus h prime again is the derivative of this whole thing. And remember that h is a function of x. So for example, this is your y0, and this is your y0 plus h. So what we'll do is we can distribute the derivative because the derivative is linear. And so we have that this is y prime plus h prime. And what I'm going to do is I'm going to rewrite y prime is equal to z, because one of the things about the Euler Lagrange equations is that you take the derivative with respect to y prime and you consider y as being constant, which I found really weird at first, but it's really better to think of this as being an independent variable z, and that way, in my opinion, it just makes more sense to take the derivative. So anyways, here what we can do is, because you have an integral, the difference of two integrals of functions, you can just sort of combine these two and say that it is the integral of the difference of the functions, right? And we want to express this in terms of like something to do with h. So the way to do that is you say that f of x, y plus h, and then z plus some other function, let's call it g. This is approximately equal to f of x, y, z plus h times the derivative of f with respect to y of x, y, z plus g times the partial derivative of f with respect to z of x, y, z. Okay. Okay, I'll actually write out some of the other terms. Plus 1/2 h squared partial second f by partial y squared plus hg partial second f by partial y partial z plus g squared partial second f by partial z squared. Okay, so what I'm doing is here I'm considering x, y, and z to be literal like points. Like I'm not considering y to be a function or z to be a function. I'm just considering each of these to be points in three-dimensional space. And I'm considering h and g to just be real numbers. So they're not functions, they're just numbers. And this is actually the extension of Taylor's of a Taylor series, right? So this is essentially saying that like this partial derivative you get by considering x and z as being constant and differentiating with respect to y. And this you consider by taking x and y to be constant, differentiating with respect to z. And then the same thing for these higher order terms. And so this is saying that you sort of increment in the y direction by h. So we're sort of going to take the linear change, which is represented by this in the y direction, and multiply that by h. So this is like sort of h times delta f. And this is g times delta f by delta z. And h is actually h times delta f by delta y. And you add on other terms. So here, let's consider this now as being functions again. So we're going to replace g by h prime. And we're going to say that this is, yeah, that's still z. But g is h prime now. This is going to be h times h prime. It's going to be h prime squared. And now we're considering it sort of as functions, but we're evaluating this at each point. And what we can also say is that the difference of these two is approximately equal to this stuff. And now what we can do is we can integrate both sides. So we can say that the integral of this from a to b with respect to x is equal to the integral of this with respect to x plus the integral of all of this stuff with respect to x. So from the conditions that delta j of h1 plus h2 equal to delta j h1 plus delta j of h2 and delta j of alpha h is equal to alpha delta j of h, you can check that this first integral satisfies both of those. So the integral I'll write down here. This is actually what's going to be our first variation of our function, which is the integral from a to b of h times derivative of f with respect to y valued at x, y, z plus h prime times the derivative of f with respect to z valued at x, y, z again, and integrating that with respect to x. And so remember that z is secretly your y prime, but we're just calling it z here, and we're considering it to be a completely different function. And so these terms, you can say it's like an integral of h squared, and this is almost like h squared is h times h prime. This is also almost like h squared. Again, so that's what I mean by like these are quadratic or higher in h. And this actually satisfies that it's something times the magnitude of h, where that something goes to 0 as the size of h goes to 0. So that's saying like epsilon goes to 0 as magnitude of h goes to 0. So this is essentially saying the same thing as like quadratic or higher in h, and that's what these are sort of explicitly being quadratic or higher. And so what we're going to do now is focus on this guy and set this guy equal to 0. So yeah, let's do that. Okay, so here we have that this expression is equal to our first variation, and remember we're focusing on sort of our increment, or sorry, not our increment, our augmentation of our function, so like the difference between this line and this guy, and that is delta j of h, and we want to sort of set this, which is our first variation, equal to 0 for all possible h. And I said in the last bit that it's actually for all small h, but in the errata video, I'll show that if it's not 0 for any h, then you can find an arbitrarily small h. So basically the idea is that this must be 0 for all h. So notice here that we have this h prime, but we don't like h prime. We want to, it would be nice if we can sort of factor this as h times something, right? So let's focus on this integral. So we have the integral from a to b of h prime times partial f partial y dx, and I won't bother in writing in x, y, z because it's implied that this is just evaluated at x, y, z, and again z is y prime. I'll just keep saying that. And since we have the derivative of h and we want to sort of integrate that, the way to do that is integration by parts. So notice that we're integrating with respect to x, and here h prime is equal to dh dx. So remember, h is just some function of x as you have here. And so this is equal to h times partial f by partial y, valued a, b, minus integral from a to b of h times d by dx, partial f by partial y, dx. Now this is a total derivative, not a partial derivative, because we get it from integration by parts. So maybe I'll do some more examples about why that is. These are all z's, not y's. So yeah, maybe in a video with a bunch of examples, I'll talk about like that this should be a total derivative and not just a partial derivative. Although it should also be clear from this example what I mean by that. And so this is h times something, right? But we have this pesky little thing in our way. So what we're going to do now is we're going to sort of think about these two boundary conditions. So let's call like y0 is our original function, right? And we have that y0 of a is equal to a, y0 of b is equal to b. And let's say that we have y1 of x is equal to y0 of x plus h of x. So h of x is your augmentation, and then this function up here, which is y0 plus h, we can rewrite that as y1. Now we want y1 to also have the same endpoints. So we want to say that y1 of a is equal to y0 of a is equal to capital A, and y1 of b is equal to y0 of b, which is equal to capital B. And so now we can sort of use this right here to say that, for example, if we look at this one, we have that y1 of a is equal to y0 of a plus h of a, just by using this explicitly. But that should be equal to y0 of a because of this condition. And based on that, we can see that h of a must be equal to 0. Similarly, using this condition, we have that h of b is equal to 0. Now this will just be h evaluated at b times some garbage minus h evaluated at a times some garbage, and both of those are equal to 0. So this whole thing is just going to be equal to 0. So this is again like h of x, this is delta f of x, y, z. Alright, so as I was saying, this is some h of x times some derivative of y with respect to z, and that's just h of b times some garbage minus h of a times some garbage. And h of b and h of a are both 0, so that means that this whole expression is equal to 0, which means that we can sort of get rid of this. And we can say that this is equal to negative the integral of h times the derivative with respect to x of partial f by partial z, and I'll sort of bring this negative sign here. So that way, we can write this thing as being minus h times d by dx of this guy. Now we can do something further. We can actually factor out the h from both of these terms, and we can say that this is h times this whole expression. Now for this to be 0 for all h, and I'll explain this further in the errata video, it actually must be true that this inside bit is 0 for all values of x. And so obviously if this inside is 0, then the integral is also 0, but it also goes the other way around, that if this integral is 0 for all possible functions h, then this inner part must also be equal to 0. So what we have is partial f by partial y of x, I won't write that down, minus d dx partial f by partial z is equal to 0. So this right here is what is called the Euler Lagrange equation, named after Euler and Lagrange. And so this actually plays an important role in Lagrangian mechanics, which is pretty cool if you have not seen that before. But the way that this is usually written is partial f by partial y prime. But this always bothered me because it's like, how can you sort of fix y prime and change y, which is what this is representing? Or how can you fix y and change y prime, which is what this is representing? But the better way to think about that is just sort of these are increments in these guys, and you get that from expanding out like a Taylor series and working with that. Anyways, let's use this equation with these boundary conditions to finally get the thing that we have, the line function of least length between two fixed points. So again, if j is equal to the integral from a to b, f x y y prime dx, then we have that partial f by partial y minus d dx partial f by partial y prime is equal to 0. And again, I'll write this as z because I don't like to think of it in terms of y prime, even though I will in later videos. But in this case, we have that f is equal to the square root of 1 plus z squared. So notice that there is no y, so this term is equal to 0, right? And then you have minus d by dx times the derivative of this with respect to z, which you can pretty easily check is equal to z over square root of 1 plus z squared is equal to 0. Now we can substitute back that z is equal to y prime. So that's what it's really meaning by saying that you take the derivative with respect to y prime. So this is equal to y prime over the square root of 1 plus y prime squared. And the derivative of that is equal to 0 because you can just multiply both sides by -1. And so if the derivative of something is equal to 0, you can, you know that the thing on the inside is equal to some constant. So you have that y prime over square root 1 plus y prime squared is equal to some constant. Or you can explicitly differentiate this with respect to x and use chain rule, but this is much easier to do. And so here we can see that we have y prime is equal to some constant times square root 1 plus y prime squared. Or we can square both sides and we see that y prime squared is equal to c squared times 1 plus y prime squared. Or you can sort of isolate y prime squared and say that y prime squared is equal to c squared over 1 minus c squared. So that's just taking this to the other side. And now we can take the square root of both sides, and we have that y prime is equal to square root of c squared over 1 minus c squared, which we can just call some c prime, right? So c prime is just some constant, right? And that means that we can integrate both sides with respect to x. We get that y is equal to c prime x plus c double prime, I guess. And so what are the values of c prime and c double prime? Well, that's based on your initial conditions here, which is y of a is equal to a and y of b is equal to b. So if you want to do it out, you can say that this is equal to b minus a over b minus a times x minus a plus a. So you can check that this is just some constant times x plus some other constant. And if you plug in x is equal to a, then this will give you capital A. If x equal b, this will give you capital B. And so that is our solution to the thing. Okay, so to recap, we start off with a set of functionals, which or a set of functions, which is all functions that satisfy y of lowercase a equals capital A and y of lowercase b equals capital B. From that, we said, okay, we're going to construct this expression, which is the integral of 1 plus square root 1 plus y prime squared dx, and that represents the length of the function if like the function is represented by a string or something. Then we said, okay, we're going to expand this. We're going to sort of change y of 0 by a little bit. So, for example, you can change it by a little bit and like that, or something like that, or something like that. So you change y0 by a little bit, and you see, okay, how much does the arc length change by? So this is the arc length of your new augmented curve. This is your arc length of your original thing, and you want to express this as some sort of change, which depends on your augmentation, plus something that is much smaller. Then we said that if this y0 is an extreme value, then this must be equal to 0 for all values of h. From that, we derive the Euler Lagrange equation by expanding this out through a Taylor series and making some simplifications. And then we use this Euler Lagrange equation with this function square root of 1 plus y prime squared to finally get that y must be a straight line that connects these 2 points. Whew, okay, so that is it for the example, and if you want to go back and watch the abstract garbage video again, you can, and hopefully it'll make more sense if you sort of think of these ideas now.